Pleasure to present Hans Wenzl, who will speak on subfactors related to certain symmetric spaces.
Okay, all right. Okay, thank you for giving me the opportunity to speak here and for to the audience here to come. Yeah, so it's so essentially, it's this is about a project generalizing a very basic subset, namely if you have H and G set X as say for simplicity finite group, then of course say we have outer actions on say let's say the hyperfinite for simplicity, then of course one of one's first examples of subfactor was just you look at a fixed point algebra of T in H, and we get a subfactor which has index H or T equals T the root index, and and the principal graph is just the induction-restriction graph between the representations. So here the attempt now is to try, well of course we could do it for Lie groups, say, but then we would get infinite index, and so that would be, I mean, it's of course interesting in its own right, but I'm more interested in finite depth. So the question is, can we do this? Can we do something similar for fusion categories? And of course, by this I mean the one which you get either from loop groups or from quantum groups, which are quotients. And so, I mean, for fusion, I think, so I wasn't quite sure how much I should talk about this, but, well, okay, let me first of all, if you have an abstract tensor category, what would be sort of, how would you think of sort of some sort of subgroup category? So of course a categorical formulation is the following. It's just you can view rep H as a model category of rep T. And about the most trivial thing, namely, say if W is a representation of H, and okay, this is in rep H, and say V is in rep G, and what's the module action? Okay, M means sort of the module action here. It's just the most trivial thing you can think of. It's just W and the restriction of G, which of course is again in rep H. Yeah, so that's so in that sense, we have the following categorical formulation would be. So we can rephrase the question the following. Find module categories of, say, some fusion ring which somehow resemble some embedding of Lie groups. So, of which resembles embedding of Lie groups. And now here I will be more specific because this is actually where I sort of could work this out specifically. Here, say SON into SUN, and it also works for SPN. And I mean, I had sort of this name sort of symmetric space in the thing because as I hope this would be for anything what is the fixed point algebra for order 2 automorphism. Now, as it would turn out, this is kind of related to what Roberto and Katze and she did, and also with this orbifold things and this thing. So all right. So Okay, now I come here from the quantum group setting. So the first thing, of course, is from the quantum group setting. So the problem is, that UQSON does not embed into UQSON. Yeah, so one can use quantum groups to construct these fusion categories. So one needs a kind of different approach. So okay, all right, let's see what. So okay, let's go more specific. So I'm. Okay, I guess I would have to. Okay, okay. So we try a very naive approach. Let's just you try to deform the embedding sort of. Let's say categorical thing. Sort of deform embedding of SON into SUN. So how does this go in the classical case? So what we do, let's say B equals Cn, the vector representation. So then we look at and SUN, B times n. Of course, this is just equal to some quotient of the symmetric group. And I put a bar here just because it's usually it's not the whole symmetric group. So this is embedded as SON is a subgroup. This is embedded in SON, B times n, which is equal to some Brouwer. This is called the Brouwer algebra. BR so n, which depends on the parameter n corresponding to the dimension. And I don't know. Okay, for those who are not familiar, you can graphically represent the symmetric group, say here via graphs, where say here is I and here's pi of I, and the extension is here that you also allow horizontal edges, like something like this could be allowed. And then the multiplication is just given again. You stack one graph on top of the other one. And if you get cycles, you just take them out. So a multiplication is just stacked on top of each other, and then it's just the product equals just graph. It's just n to the number of cycles times the rest of the graph without cycles. Yeah, so maybe as a simple example, if you do if you multiply this one with itself, so you connect them, and then you have one cycle. So this is n times this thing here. Okay, so this is started. So this is the classical situation. And so we could do this. We could form inductive limits and take the closure, and we would get sort of embedding, but which would give us infinite index. So how do we do the deformation? So then we have here n UQ SLN V tensor n. Now this is known. This is as a model to some version of the Hackey algebra H and Q. So the Hackey algebra is just the quotient of the break group, and where the break generator satisfies a quadratic equation. So this is well known. So hence, what we would like here is we would like to get a deformation of this thing here, which contains the Hackey algebra and satisfies certain compatibility equations. So maybe now I go back to the other one. So what we need, okay, I think, so need deformation of let's call it dr, whatever, n, maybe n and the q of the Brouwer algebra. So such that it contains the Hecke algebra Hn, it's a subalgebra, and moreover, so the Hecke algebra has a canonical trace called the Markov trace, which essentially is a dimension function for this. So it has a trace which it can tr extending the Markov trace on Hn. And finally, there should be compatibility conditions, which is usually called a commuting square condition. And basically it just means that okay, let me just write it down and then I'll explain. So the conditional expectation is just an orthogonal projection coming from the trace bilinear form. So if I apply this to the Hecke algebra Hn, and I project onto the n-1 subalgebra of the Brouwer algebra, and get Hn-1. So here, E, let's call it some A, equals orthogonal projection onto subspace A, whatever, I guess in Brn. So I leave out the indices here. With respect to the bilinear form coming from, okay, maybe I just write it sloppily with respect to TR. But this, I mean, I look at the, whatever, inner product, the bilinear form coming from the trace. So it's just GNS construction. Okay. And so it turns out this essentially then forces the relations. So then when I'm not going to, the relations are not overly complicated, but not terribly intuitive. So then forces relations. So basically we have generators T1, T2, Tn-1, this is the Hecke algebra, and one more, E, which would correspond sort of to this guy here. And well, I think essentially the non-trivial relation is essentially is the following, that let G2 be the following grade. Let me see. So it's something like G2, G3, G1 inverse, G2 inverse, or something, if you write it. So then the relation is that let's take E2 to be E, G2, E. So that's essentially, if you draw the picture, it would be something like, so here we have E, then we get like this, so it's something like this. So essentially you should think of it just as something corresponding to this guy here. Then it should say that G2, E2 equals E2, which is equal to E2, G2. Okay, maybe a comment to this is, so the problem here is, in general, in the Brouwer algebra, this thing here is well defined in the classic one, while here it's not really well defined. So because you know, in general, well, if you take now this other Q deformation of parallels, the BMW, there you just conjugate via the brace, and then you essentially get a unique element of this form. Well, here one has to be careful, so one has to take this. So for instance, this is not equal to this thing here. Yeah, so you can't really use graphical calculus here. I mean, I just use this as abbreviation for writing this expressions. So yeah, so anyway, so you know you get you just get some relations and one can work with them.
But you told us that you have only one mode generator.
Right. There's only one more generator, which is not surprising because in the classical case it's the same thing. So it's okay. Anyway, so we get something. So interestingly enough, you know, I thought already, well, we have two deformations, but then Zheng Weiliu, he wrote a recent paper where he gets yet another Q deformation, which gets I think some other symmetric, well, something like a conformal inclusion. I think he told me, I don't think the paper is written yet interpreting the subfactors he constructed and the thing. So there exists. So it seems this is not the only one, but anyway. So all right. So anyway, we get this. So now we are in at least as far as I'm concerned with what I have been doing for a long time. We are in a good setting. We're getting sort of sequences of algebras. We have the commuting square condition. So as long as we can find a positivity in C star structures, we should get a subfactor. So we have now a okay. So get subfactor. Okay, so assuming C star structure and positivity, we get subfactor so we do G and S construction, H infinity, and find dr infinity of M cubed. Okay. So now, of course, the question is, yeah, when do we get the C star structures and then, of course, can we calculate indices, etc.? Let me see how. So yeah, so this has been worked out. And so the
C star just means star involution now?
Yeah, star involution and positivity. I mean,
no.
yeah, you know, it satisfies this the norm. Yeah, yes, of course. And you know, the usual thing like A star A equals A squared. I mean, yeah. So we have a norm on it, and which that this is all satisfied.
Because you go to the GNS representation anyways.
Yeah, I mean, okay, all right. I'm a little sloppy here with it. So what? Yeah, one has to be somewhere a little bit careful there. So it turns out, yeah, normally what you do. I mean, this Markov trace is defined, always defined, whether there's a C-star structure or not.
Mm-hmm.
Then also you can also do essentially the GNS construction, also it's just in a purely algebraic way. And so then you look at the quotient of this,
yes.
Because in general you cannot define a C-star structure on the whole thing, anyways. So, but you get a then it turns out here, for good values, you get a semi-simple quotient,
Mm-hmm.
and of course the C-star structure should be the obvious one. I mean here, like, well, oh, okay, I just erase this. So we have generating relations. So of course we have a GI star should be GI inverse. Well, at least for Q root of unity. And for Q real, you would have it solved, but and E star equals E. Yeah, see, we want this, and so and then we have to check that this does define a C star thing. For instance, this only works for special roots of unity. And because, for instance, for the wrong root of unity, you might get some elements of the form A star A with negative spectrum. So of course that wouldn't work. So anyway, there's some working out things to do, but this can be done. So then. Okay, so then we get the following theorem. Yeah, okay. So there exists C star structure, whatever C star structure plus positivity. Well, I mean, something it's sort of the same. If for n in C, I think n not equal to a negative odd, and Q equals e to the plus minus pi over L. And so essentially, the even odd corresponds to symplectic ones, and the positive corresponds to orthogonal ones. So n a negative odd, a negative even corresponds to SP n in SUM. But I think I'd probably just stick to the orthogonal one. So, and okay, this is one thing. So now, what's the index? Yeah, for the index, it's a little okay. So let me write it down in a general form, which then would suspect, this could be done in even, this formula like this should hold in even greater generality. So the index given as follows. So let me just do it in general for K and G, K and G, and here K equals either SON, SPN, and G equals SON. So, okay, first of all, what we do, G, of course, we can view G as a model of the subalgebra. So we have, so G equals K plus P, and I assume, I don't know whether it's necessary to assume P irreducible. In these cases, it will be irreducible as K modulus. Then the subfactor would be given as the index of the subfactor and n is given by. All right, so here this is either just 1 or 2, which is depending on the Lie type. L, this is this L here, times NP. So this is just the multiplicity of the zero weight in P. I'll write it down after. And let me omega equal to 0 of 1 over 4 sine squared omega rho at pi over L. Okay, so let's say again, so BK, this is I do not understand whether it's why it's 1 or 2, but it's either 1 depending on the lead type. Then NP equals the multiplicity of 0 in P, which if you think about it a little bit, this is just equal to the difference of the rank of G minus rank of K. Okay, and what else do we have? Oh yeah, the omegas. So here this product goes over the weights in P corresponding to positive roots. So let's just P corresponding to positive roots. And let's see what else, a row. And a row is half of the sum of the actually of the co-roots. So if it's non-simply laced, so it's row is half sum of co-roots. So it's not the usual row, which would be, well, of course in the simple laced case it wouldn't matter, but anyway, this is just a minor technicality. Okay, so at least in these cases one can all write it down like this. So maybe we should write down some explicit and do some examples. The first example is kind of it's kind of a fake example because in some sense SO2 isn't really a Lie group, but it's very easy. There's SO2 into SU2. So then here, okay, so SO2 basically is the torus of this one, so they have the same rank. This is 0, and then of course we have. So if we view this, the rest here has 2 weights. So we have 2 weights left. One of them is positive. So here, hence the index is just. It turns out it's just 1/4 sine squared pi over L. Sorry, it's 1/2 because here the b in this case for actually I can say so it actually bk is equal to 2 for SO even and 1 otherwise. Anyway, this I mean I don't know why, it's just what the calculation turned out to be. And it turns out these are well known. They correspond to the Goodman-Delahaye-Jones subfactors, which at least for people who know about them. And this is so they are so they were constructed like 30 years ago by some elementary methods. So all right. So then let's do something a little more. What about SO3 into SU3? So then if you look at the formula, so then SU3 has dimension 8. So SU3 which corresponds to SO3 plus P, which is the 5-dimensional representation, just by dimension count of SO3. So it has a 1 0 weight, 0, and then weights plus minus 1 plus minus 2. So we get this index equals and the rank, this has rank 1, this has rank 2, so we get 1L over sine squared pi over L. Okay, 4 sine, rather we have 2 4, so 16 sine squared pi over sine squared 2 pi over L. Okay, now when I wrote it down and found Friedrich, I said, okay, I got the same formula. Well, it's actually almost the same formula because he got it from this in this affine orbitals where you have an outer action of C mod 2 acting on acting on SU3, and he got the same for with the factor 3 here. So they got the same. And I think I sort of understand this. Why? Because in this construction, you actually should view it not so much as a module over SU3, but over PSU3. So you only get 1/3 of it. So I thought they're closely related. So I would suspect this guy here is an intermediate subfactor of the other one here with index. Yeah. So all right. So now. Okay, another thing now with this method is we can actually also explicitly describe the principal graph. So the principal graphs are essentially just truncations of the induction-restriction graphs. So, and yeah, I don't know. It's probably not that helpful if I draw this graph because I mean,
They finite left.
oh yes, they're finite depth. So. And so, yeah, so basically, well, one can sort of explicitly say, because, so for instance, for SU3, so if you have here the Weyl chamber, the truncated Weyl chamber here, then I think that's just, now I think there exists probably a more conceptual saying in this, in the Kac-Moody algebra approach, which I think are just the fixed points under the Zima-2, which maps the representation to the dual ones, so the self-dual representations. But one can do it also. So in my case, they are just the ones which correspond to Young diagrams whose number of boxes is divisible by 3, which would be the ones corresponding to PSUN. And so that's why I don't have the factor 3 here in my case. And the ones from SO3, yeah, I mean, one can also figure out that there's finitely many for SU3, which depend on the rule of unity. And so, and then what you do, you just calculate the induction-restriction rule, calculating, essentially evaluating here at this element here to get the quantum traces. And so, in general, what happens is if you are very close to this hyperplane, usually some of the restriction, the multiplicities of the smaller one will are smaller, which is the usual thing. What happens is, let me just be a little bit vague about it, what this is, because so let's say the principal graph for this. So we have the given by modified induction restriction graph for SO and I guess in our case to SUN. So basically, yeah, what you so essentially means if L goes to infinity, then you get it will approximate the classical restriction graph. The classical restriction graph for this one here. Yeah, because I mean basically then, so that means if you let this go up, then as I said before, like for this one, if it's near this boundary hyperplane, then the multiplicity or will be smaller, like the S. Yeah. So okay, the way you can do it, what you do, you take this guy, restrict it to SO3. You get a bunch of representations, but it will turn out that some of them are not allowed by in this thing. So then you reflect them back into the allowed ones with a negative sign, and then one can show that you will still get positive multiplicities. So that's. But if your guy here is far enough from this one, then if you restrict the thing, all the ones will be allowed. So that means if you're far enough from this one, you will get the classical ones. And if not, then you have to do some correction terms. But this is kind of standard stuff. It's similar, like for instance, for the if you look at the tensor product rules in the Western, in the Whitmore, or in the fusion rules, they also, I mean, you have to you apply the affine Weyl group to this, and you get some corrections. So it's similar thing here. Okay. Another thing what you observe is also, if you look at this thing here, so here we have the number of positive roots, and if you count this, anyway, this is a very simple calculation. Then you see that if L goes to infinity, the index goes to infinity with the asymptotics of, okay, so if index goes to infinity with asymptotics to L to the dim G minus dim K. So that's very easy to see from this formula. Okay, so I think maybe this approach has, I think it's some advantage that, because I think he did some calculations and he calculated for SU3, but in general it seems to be hard to explicitly calculate this stuff. It seems in this approach it seems maybe somewhat easier to do these calculations, but okay. Now the disadvantage of this approach is so far, at least this approach which I told you, deformation this thing with bare bones, I can do it for these two particular examples, but for other examples it seems to be kind of hard. So the question is, can we do it for what about other symmetric spaces? So, I mean, in this approach. Now, there seems to be, let's see how much time, I still have plenty of time. So, I mean, there seems to be a way how to do it more conceptually, by even in the quantum group setting. So, as I said it before, UQSON, the Drinford-Chimper quantum group, cannot be embedded as a Hopf algebra into UQSON. However, there exists another Q deformation of this, UQ prime SON, which does embed into UQSON as co-ideal subalgebra. So this means, of course, that okay, so of course that means if you apply the co-product, SON is contained in, well, let's UQSON contains a UQSON. So hence, that it's obvious now that rep UQ prime SON is a module category of UQSON. Yeah, in the obvious way, because if you have your W tensor V, yeah, if this is in SO prime, and this SON, this is still, using the co-product here, this is still an SO prime module. Okay, so, and I was hoping actually that, and of course, this well, maybe I should mention this have been defined, let's see, I think as letzte, Numi Sukatani, and I think as a clinic, and maybe others studied this one. So there exists sort of like all kind of papers about quantum symmetric spaces. So, and in principle, this is very suggestive that this should work in general. But I mean, well, I haven't looked at it in a while, but what seems to be kind of hard here is really defining the C-star structure on this thing. Yeah, even it's just playing around, even in this sort of most trivial case, SO2 into SL2. The naive approach to how to define the star structure seems to be very complicated. So I think I'm missing something. So, but I hope I can revisit this and understand this better. So the hope would so this co-ideal algebras, sub-algebras, have been defined for all symmetric spaces. So the hope would be that using some addition of a machine like this, that it may be possible to extend this construction here to more general, to more general setting. So, but this is generalization. So I don't know. So all right. So okay. I guess I went maybe fast, or I didn't prepare more. So I could just, if you want, I can just construct some graphs. Maybe just if I just worked out some for SO2 into SL2. This, of course, had already been found by Okamoto a long time ago. Except it's impossible to find this paper. It just appeared in some book, and I haven't found it on the internet. So that have been so they have been done by him, but I haven't been able to look it up. But so for L equals, I think the first non-trivial L equals 6, where it's just the index is 2, so that's very easy. For L equals 8, we get the A7, the graph A7. So that's still easy. For L equals 10. That's the first kind of interesting one, and that was actually kind of interesting for me because, okay, here we are. Oh, okay. So where are you guys? Okay, yeah. So this is something like this. Okay, now this graph has 3 plus square root of 5, which is kind of interesting at this time because I think this is as far up to this index. So I think subfactors have been classified up to this index value now, and this is what is one of these fish graphs, which then has and I think there was originally then an infinite series of graphs like this, where you just, I think what you do, you just push it out and then you add some of these spines to it, and then I think Cheng Wei showed that only originally it was conjectured that a subfactor would exist for all of this, and Cheng Wei Liu showed it's only for 3, I think, for 3 or 4. Of this graphs, we have a subfactor, and for others we don't have. So, but I didn't know, and this also appears as this is 2 times 1 over 2 times 3 plus square root of 5, where this is which are the 2 smallest non-trivial index values for subfactors, and it appears as a free product of A3 and A4. So that's this one, and then. Yeah, so another one that for L equals 12, that's still a nice one. So that's so because this one can still be drawn in a planar way. Okay, so this is for L equals 12. Right. So these are all for O2 and to SO2, and then I think maybe I do one for SO3. Which, okay, maybe I have it. Oh yeah, here there it is. So it is. This is for ninth group unity. Okay, and then now this could be, so this is a case where we have a non-trivial orbital, so maybe at some point I was speculating maybe there should be some orbital construction, but I think, now I have the feeling it doesn't work, but I have not gone that much into this, so. Anyway, so one can play around with this stuff and one can construct things. And okay, I think, yeah, I guess I haven't prepared more, so. No, okay, maybe one more thing. Which I actually did prepare more, but it's just, yeah, so also, for instance, this one's for SL3, they also did like, in Dianes and collaborators, they construct also look at there's model categories for SL3 and looked at the NIMRAPs. That means essentially you let the generating object for SU3 act on the objects of SO3, and then that corresponds to this graphs. So depending on L, you get more and more of this, which are basically just tensor product rules of SO3. So if you look at that of truncated SO3, so they also appear in this, but I do not get these ones here. They also have these ones here, and they would, it seems they would correspond to SPN, SP2 into SU3, where the three-dimensional decompose into trivial plus two-dimensional of this one. But I do, again, so my construction doesn't work for this case, at least not so far. So okay, I think that's it.
Any questions or comments?
If you start with the finite groups, can you play similar game?
Sure.
You get the classical one.
Oh yeah, that's for finite groups. It's that's known. It's because this was one of, yeah. So you mean, of course, here the fusion graph is just. I mean, for finite group, it's just what I told you once. Same thing that like R G and RH. And so the first principal graph is an induction-restriction graph. The dual principal graph is somewhat complicated.
You get only one solution.
Oh, now I think there may be one, because I think you can twist this by cocycle, so I think, yeah, because I think it corresponds to the projective representations of the subgroup. Yeah. I think, well, okay, I don't know, I don't think this can be seen on a level of subfactors. It's just for the, if you do it in the category, people just told me, I think if you view this as a, rep H as a model category over G, then and you want to classify them, then I think it boils down to that it is, and I think maybe one can even show this, that any model category over a finite group that corresponds to a subgroup together with some maybe cocycle, which giving you projective representations. So I think for finite groups this has been, this model category has been classified. Yeah, now I think probably the more conceptual one is the thing what about modular invariance and the thing that maybe, but which That's how the ones have been classified for SU3, of course. But I guess the model invariants they are really not strong enough for getting everything. Or I think that's just too many for SU4, SU5. But I haven't looked that closely into this, so probably Dai would know more or Gannon.
Only vaguely related question. Namely, when you don't start with Hecke, but ask for some higher polynomial relation for the generators, like third order or something like that. Is that investigated too? Or?
No, but I mean, it's just, I mean, of course, that would mean like you want to study model categories for SON, and the thing, and that's more complicated. So I mean, no. But you know, at some point I was thinking about it, but it looked like because the problem is now the model categories are even more complicated. You know, at the moment I can't even do all of the, at least with this naive approach, which I used here in this case, I can't even do all model categories for SUN yet, while I still have this thing. So it's so then so I would assume like for SON model categories over SON would be even harder. As I said, my hope was really that you know, using this coordinate algebras there may be a general approach, but this is a. And anyway, I want to revisit this again. I mean, and hopefully look at reading a little bit more about this thing, and because when I first tried it, I was really very naive, just playing around, and so, but not using very much of the structure theory of what is known about this. So hopefully. Understanding this coordinate is better than hopefully there's some chance of getting more results. But yeah, I don't know. It may just be that I mean the naive approach that just didn't work hard enough. So that there could be. I mean, yeah. I mean, okay.
No one else? Then let's thank the speaker again. There's the cake and coffee and tea over in the main building.